Okay, now it's time, and let's start the last lecture today, which is about deep learning framework on Fugaku. Okay, before we start the lecture, let me briefly introduce myself. My name is Kento Sato. I am a team leader of high performance big data research team at R-CCS. Basically, I'm also not AI expert. Basically, our team is developing system software for large scale supercomputer, especially to enhance the performance of I/O performance on Fugaku or other large scale system. So today, this is the agenda for today. I think my face cover the screen, so let me turn off the video so that you can see the order of the words in the slide. And this is the today's agenda. So in this lecture, you learn how to use one of AI frameworks, PyTorch on Fugaku, and especially you learn basics of how to use tensor operation on PyTorch and Python, and how to load a dataset with data loaders, how to build a neural network, how to train neural networks. So today we only have 1 hour and 20 minutes. So I may not be able to cover the rest of the talk, agenda, but if I have time, I will also lecture about how to save and load a trained neural network. And I'd like to lecture how to extend your code for distributed training. And also there is several exercises, so I hope you can join for the hands-on exercise. And also, so the remark is, I give this lecture first time, so it may have some bugs in the slide and example code, but please be patient and forgive me if there are any progress during the lectures. So again, so before the lecture, please prepare for the hands-on. If you haven't logged into the Fugaku node, please log in using SSH. Then maybe you want to reserve the interactive node first by running this command that I announced in the beginning of the previous break. Then please run this command. So I'm going to show you. Right now I just logged in and it's empty. I think should I make it a little bit bigger? Okay. Then I'm lazy, so I just copy and paste. Make a folder for this school. Then get the toolkits, the example code from the GitHub. This. If it's too early, just let me know. I try to periodically check chat box. Okay, then go to HPC2 example, and there's other like example code, but today we learn about deep learning. So please go to deep learning, then PyTorch, Fugaku, and basics. It has several example code that I use, that I give a lecture based on. Okay, I hope you're ready. Sorry, it might be too hurry, too fast. If you want me to wait, please write it on the chat box. But I will give some time later, but so please wait for the first exercise. I give some time. Okay, today as I said, today we will use PyTorch. Basically, both PyTorch and TensorFlow are very mature frameworks, and their core deep learning feature overlaps significantly. Essentially, these are the same, but API is different, but essentially the same. But PyTorch has become like a de facto research framework after its explosive adoption by the research community. as you can see from this graph, the first in the beginning, like in 2017, PyTorch was a major framework, but it's being replacing the PyTorch with TensorFlow, and PyTorch is becoming more like a major framework in the research community. I don't know about the industry community, but this is a survey from the paper. The survey paper, which the survey about which framework is used in the research, and the number of PyTorch use case is getting larger and larger. So we use PyTorch in this lecture. And so before you use PyTorch, you need to set several environmental variables as shown in this example code, but it takes time. You can copy and paste, but much easier way is to run this script. So this script is on one upper directory, this script. If you wanna see the inside, it's what I specify. This is what we specify for the environmental variables. And please ignore this line. So if you use Emacs, it crashes without preloading this library. So if you're a Mac user, just simply run this script before you start the exercise. Then now it's ready. You're ready to use PyTorch. Okay, so before we teaching about how to use AI framework PyTorch, I will briefly teach about tensor operations and tensors. Tensors are specialized data structure that are very similar to arrays and metrics. In PyTorch, you use a tensor to encode the inputs and outputs of a model, as well as a model's parameters. So tensors are like NumPy. If you used NumPy ever, it looks like NumPy. But except the tensor can run on GPUs or other hardware accelerator with the same interface. So if you use NumPy, it doesn't work for GPU. You have to import CuPy if you want to use NumPy on GPU. But if you use tensor provided from a PyTorch, it can run on CPU and GPU and other accelerators. So this is example code. So this is how to use tensor. So you need to import torch, and you define, create a two-dimensional matrix 2 by 2. Then in this line, it convert the regular array into tensor type. Then what it does is just print the internal of this data structure. This example is directly convert the regular array type into tensor type, but you can also convert the NumPy array into torch tensor type. And then by defining the tensor, you can easily compute matrix add or matrix multiplication by simply use coding a plus or this asterisk keyword. And okay, so this is our first exercise. By looking at this test code, please try compute the following tensor operation with tensor data type. I will give 1 minute. So because we have a limited time, so I just give you 1 minute. Okay. And so if you are lazy, you can again, if you don't want to do a hands-on or you don't want to type, the answer is inside this script. So if you just want to know the answer, you can just look at this source code. So just you can just use Python import Then you create. It takes time. So importing a torch package, it takes time. So yeah, it's loaded. Then you define create a matrix. The first one is 1, 2, 3, and the next column, next row is 1, 3, 4. And the last row is 3, 3, and 4, and 5. So you can it. So you can define the regular array, regular matrix. Then you have to convert this. You can just I want to use just a convert this array from regular array to tensor type torch. Okay. So this is array. So print looks different if you use tensor type. It's more easy to see as a matrix. So now it's tensor type. So you can use like this. You can use a computer matrix add and matrix multiplication like this. Yeah, this is the answer of this exercise. So again, you cannot do like this. I think you can do this. Yeah, but if you do this, it doesn't calculate. It just append the array each other on this side. So it doesn't calculate the matrix out, even if you do this. It gives error if you don't use tensor type. So this is how you use tensor operations. So now we move on to the how to use PyTorch. So in PyTorch, there are 3 major components: neural networks, data loader, and optimizer. Neural network is to define a class and implement neural networks that you want to train or you want to use for prediction. And data loader is an interface to a dataset for training and testing. And optimizer is to optimize the parameters of a defined neural network that you want to train with dataset. This is figures to summarize these 3 components: data loader, and you feed the training data to define neural networks. Then externally, the optimizer optimize the inside parameter of this neural network. This is how PyTorch works, and also this is also almost same to TensorFlow. Before we learn how to build a neural network, let me explain about datasets and data loaders. So dataset and data loader is for decoupling data processing code from model training code for better readability and modularity. And PyTorch provides 2 data primitives that allow you to use preloaded dataset as well as your own data. So dataset is like defined, implemented in this package, in this path. And this dataset actually stores the data and its corresponding label, like answer. Like if the sample image data is handwritten image is 5, and then this label means store the answer. Like it's this label, this image is 5 or this image is 8. We call it label. And also dataset provides a number of pre-loaded datasets such as MNIST for prototyping and benchmarking your model, like from image dataset, text dataset to audio dataset. And also you will need to use data loader. This is a wrapper which wraps iteratable data structure to enable easy access to samples. So relationship of dataset and data loader is something like that. you get a data set and then you wrap the data set with the data loader. Then you iterate this data loader to get training data in a for loop. Okay, so first I will how to load a data set using data set, PyTorch data set. So first you need to import necessary packages. This for lines. Then you use dataset dot. In this example is fashion MNIST. This also appeared in the previous lecture, fashion MNIST. And you specify location where you want to download this training data, and you specify if this is training data or not. If you specify, you can, this is not important, but if you specify true, it give you lots of sampling data, and if you specify false, it give less amount of training data. So basically, it's not big difference. And then if you want to download, you can. Today you want to download this data set, so please specify true. And also this data set give you like raw data. It's not usable in PyTorch. So you have to convert this raw data into a tensor type, so that you need to specify to transform the raw data into tensor data. So you need to specify two tensor function to transform argument in this example. So you don't have to understand each argument. Just you copy and paste on the source code if you want to try this code. And the next exercise is please modify this 01 underscore data types dot py to download MNIST instead of fashion MNIST by referring to PyTorch API document. So MNIST is a dataset of, also it's appeared in the previous lecture. It's a handwritten digit that is commonly used for training various image processing systems like this. MNIST is something like this. And I will give you 1 minute. Sorry, it's very short. But this is you need to modify this code. This code is same as this example code that I showed in. And you modify this code to be able to download MNIST dataset instead of fashion MNIST.
佐藤先生、ケントさん。
I'm sorry.
あ、
I think I muted. So what did I say last time? What the last thing that I say? 最後に何言いました I don't remember.
we heard so we gave ourselves the 1 minute exercise.
Okay.
Yeah.
Okay. Thank you. Okay, I gave, okay, maybe we share the screen so you knew how to, you knew the answer of this exercise. Sorry, we don't have time, so I don't get back. Sorry. So before we before I explain the data loader, I will explain the overview of workflow of a training neural network. So so first it retrieves a multiple sample that we call a mini batch or batch from a data set. So in this case, it has training samples, it has a number of training sample inside. But in this case, please assume the training sample has only 8 samples like this. Then this example get only 2 images of data as a mini batch. So a mini batch is referred to equally sized subset of the data set over which the gradient is calculated and weights updated. And the number of samples in the mini batch is called batch size. So this example show the example where the batch size is 2 because each iteration this process retrieve 2 image of data every iterations. Then once you get a mini batch, it runs a forward and backward operation and update parameters of the target training neural network. Then it continue this iteration by getting batch size until train all the training sample, in this case, all the 8 training sample. Then once all the samples are fed to the training neural network, it shuffle the data set. Then repeat from the step 1. And then this, once we train entire data set once through the forward and backward operation, we call it epoch. So this illustrator one epoch. One epoch, then you shuffle, then you move on to the next epoch. Then in each epoch, when you get the mini batch and compute run forward and backward, we call it iteration. So the iteration is the number of batches needed to complete one epoch. This is a relationship of the epoch. So in each epoch, you have multiple iterations. So by repeating epoch, you refine parameter of the model and to get accurate prediction of the prediction to the images. Okay, and now move on to data loaders. As explained in the previous slide, while training a model, you need to pass samples in a form of mini batch or simply batch, and reshuffle data at every epoch to reduce a model overfitting. Data loader abstract this complexity for us in an easy API. This is how to use data loaders. So you need to additionally import a data loader package to use a data loader. Then this is how you code a data loader. So first one is data loader for training data, and the next one is test data. And first you need to specify a data set that you created from the last exercise. You simply pass this variable to this dataset argument of this function. Then you specify batch size, so that if you specify, in this case, we specify 64, so that this data loader give you a 64 image every iteration. So if you want to same batch sizes, like in this example, you need to specify 2, but the multiple case batch size of 2 is very small, so you may want to specify 64 or more for the batch sizes if you have enough memory size, DRAM memory, you have enough size of memory. And to avoid overfitting, we normally you need to specify shuffle as true. So by using this data loader, shuffle dataset, and also give you a mini batch in an easy API, and also you can iterate in a for loop. By using data loader, you can make development easier. Actually, this data loader is not necessary, but basically you may want to use this data loader for the for easy development. Then the next one is preparing data for training with data loader. So is any exercise? Okay, exercise right after this. Right after this exercise, preparing data for training with data loader. So so we have loaded that dataset into the data loader by calling this function, and you can iterate through the dataset as needed once you create a data loader. And each iteration below returns a batch of training feature and training levels. So in this example, we specify 64 for the batch sizes, so it gives you a 64 sample at one time or at one iteration. And level, each level, 64 levels. And yes, and because we specified a shuffle as true, this data is shuffled after we iterate over all batches. So this is just example. So what does this is to make a data loader iteratable type by calling it iter. Then you get the first element of this iterator. So we specified 64 for batch size. You get a batch of the 64 images. Then what we do is print size and print the levels, size of levels. Then it so this is how to get so this feature is already batches. So if you want to get the first image from this mini batch, you specify the first index. And also if you want to get the first levels, first answer of this image, you specify first index of this array like this. Then it specify this like this. If you run this code, you can get this output, I think. So because the batch size is 64, and each image size is 28 by 28. So data shape become like this. So it has 64 images, and this dimension is the number of channels. So the eminist image is grayscale. So it's just 2-dimensional images. But if it's color data, it has to be RGB, red, green, and blue format. In that case, this dimension has 3 elements for the red and green and blue. But again, eminist is grayscale, so it's just 1 element on this dimension. Then actual image is again 28 by 28, so the overall shape is become like this. And also label has answer for each 64 images. So the shape of this length of this level is 64. like this. If you print it out, it give you a answer. So first image is 5, so it gives a 5. And next image is 8, and it gives 8. So something like this. Okay, so the next exercise is get the first MNIST mini batch from data loaders and print out the shape of the mini batch, and then the label by extend this source code, like 01 underscore datasets underscore ex.py. Yes, and I will give you, I think, 1 minute. But again, the hint is just adding the code snippet on this slide. So you just open this file, you copy this, and just copy this code, and also copy this code, and paste that on this source code. Then you will get this answer, I think. If I open this code, so I also copy this. Okay, again. So all the exercise is incremental, but if you cannot catch up, this exercise is based on the extension of existing code, so that even if you start this in the middle of the exercise, you can still catch up from the middle of this lecture or middle exercise. So that if you want to, you can extend this code that you made, or if you haven't done this yet, you can use extend from this prepared source code. I think actually these two source code are same. I think they're all the same. Yeah, so it has just new line. They're all the same. So if you want to continue with your own code, you can keep using your exercise code. But if you don't want to clean up and start from the clean source code, then you can use this start with from sample code. But I will copy. Extend this. Let's extend this code. Sorry. Okay, this is this code because I copied. And you need to do is you add a data loader. But first you need to load the packages. So you have to specify this. Then you copy this data loader. But after you define this code, then you print it. So I hope it doesn't give you error. Okay, give you error. I think it like copy and paste it. So I show you in different way. In that case, so you modify this code and also write this. This is how you need to modify. Let me show smaller, a little bit smaller. Okay, so you need to add data loader here, and the code is same, and you copy and paste data loader here, and you also need to copy and paste to display the image and label. So if you run this code, it will give you the same answer. Sorry, it will give you the same output. Something like this. Yep. Then, so once you create a data loader, now it's time to build a neural network that you want to train. So neural network comprise layers or a module that perform operation on data. And the torch.nn namespace provides all the building blocks that you need to build your own neural network. So every module in PyTorch has subclass of the nn.module. So you need to make a subclass of this nn.module. So a neural network is a module. It's also a module itself, which consists of other modules such as layers. This nested structure allows for building and managing complex architectures easily. So to define the neural network, first you need to import these packages. Then this is how to build the neural network. So in this example, we just built a 3-layer linear neural network. So we call it net1. This is a subclass of nn.module, so you need to inherit the nn.module. Then you initialize the neural network layer in neural network layers in init function, like constructor. So in this, in constructor, you need to initialize layer like this. So you need to call the initial constructor or initializer of superclass first. Then you need to first call a flatten function and linear function and another linear function. So this is what we want to. This is a network that we want to build in this example. It's just simple 3-layer networks, linear network. The first, in this training, in this lecture, we trained MNIST. This MNIST has a 2-dimensional data, whereas this network is linear neural network. So you need to convert 2-dimensional data into a 1-dimensional array. So that first you need to call a flatten function. You need to flatten, and then you convert to the array into 1D array, and then you feed this array into this 3-layer. Like first layer has 784 neurons, and the hidden layer has 1000 node, and the output layer is 10 because we predict the handwritten digit from 0 to 9, so that output layer has to be 10. And also input data is 28 by 28. 28 by 28. So if you compute 28 times 28, it becomes 784. So input data also has to be 784. But hidden layer has to be any number. In this example, we use 1000, but it can be 100 or 10,000. But if you increase the number of nodes, the neurons, the training time longer, but if it give you a more higher accuracy, basically. Whereas if you give a small number of neurons to this hidden layer, you can accelerate the training, but accuracy may lower compared to the neural network. It has more neuron in hidden layers. So once you define the layer in constructor, so first layer is input is 28 by 28 and output 1000. So if you want to make this layer, so you need to define this linear layer, 2-linear layer like this. And of course, this number 1000, this 1000 has to be same because this layer's output can become an input of this layer. Then you need to connect. You need to connect this layer by passing calculate intermediate calculate variable by passing intermediate variables like this. So you call. So this is the input data, and first you call flatten, then get result. Then you pass to the next layer and get result. And in this example, we use, there are several activation functions, but in this example, we use RELU activation function. There are many other activation functions, but RELU is one of major activation function. So in this lecture, we also use RELU. Then you pass the X to the RELU and get result, and you pass to the last layer, then get result. This is you define. This is how you define a word operation like this. Then you run inference of neural network. So to run inference, before I explain how to training, I will explain how to run inference, like how to predict input images. So to run inference with a built model, we pass the input data to models. So this is done by executing the model's forward like this. So what we do is what we want to try is you first pass one image into neural network, then you code a bunch of functions, then you finally you get the answer. And I will explain how to get this answer. So by coding model on the input, return 5-dimensional tensor with low predictive value for each classes. So if you run this neural network, it gives you the array which has 5 elements, and then we reward the highest number, the index, as the answer. So for example, the first index is the highest number, then this neural network predict as this number is 0, and next index 1 is highest, it's predict as 1, and so on. So this is very simple example. So by looking at the highest index, which has the highest number, we can easily get the answer by coding argmax. But if you want to normalize this array using softmax, you can get a probability, or like in different way, it's confidence value of this output answer. So what softmax that is, so the neural network will give you like a random confidence number. It can be a minus or a positive number, but by using a softmax, it convert into a probability of this one. So in this case, 90% of this answer is first 0, and 10% in 10% the answer is the 1, something like this. But to make it more easy to have an easy answer, normally or traditionally we code a softmax, and then we get the normalized answer, and then we get the index which has the highest value like this. So in the code, we get create a model, and then you get the by passing the one image of this created image, created neural network, you run a forward function. So you don't have to explicitly run a forward function. You can just, if you specify in the argument of this model instance, then you can get the confidence value. Then you run a softmax, and then you get the index which has the highest number. It's something like this, so that you can predict or run the inference on the trained data. So the next exercise is please build network 1 and run inference of the untrained network on the first image of MNIST by extended this source code. And hint is very simple. This is a hint. The answer is very simple. You can just adding the code snippet to this example code. And I will give a few minutes. And again, this is the answer. If you don't have time, please also you can look at this answer. So again, we copy. Yes, this is the code that we use in the developing the previous exercise. First, you need to define class. I think it's not. It's hard to copy and paste. This part. Copy. Better to copy and paste little by little. Then define forward function like this. Let me check it done or not. Then I didn't import. I also need to import this one. Yes. Yeah. Let's say then it's not defined because I did not import. Import these two packages. Okay, let me test again. Then once you create it, you create. Okay, it seems running. Once you create the classes, you create an instance of net1, print it, then run inference, and then softmax, get the highest index, then print it. Of this, we just finally print this predicted value of this neural network. Let's run this code. Sorry. Yes. So the first image, the answer of the first image is 7. Then please recall, first we create an instance, then we print the structure of the model. So it output the structure of this model. The first layer is flattened layer, and then linear layer, then the next linear layer in this size. Then we run inference by calling this function. Then we print the predicted answer, but it gives 2, answer 2, and answer is 7, but predicted class is 2, so it doesn't accurately infer the image data. The reason is we haven't trained this neural network yet, so that's why it gives a wrong answer. Like even if I run next time, it will give. Sometimes it gives. If you're lucky, sometimes it gives like time to give a correct answer, but it doesn't always give you a correct answer. Like this. The answer is 9, but it gives us 6 like this. So that's why you need to train this neural network before you run inference. Now we defined the models. We have training data, so it's time to train and test our model by optimizing its parameters on our dataset. This example, we use MNIST. So training, as I explained in the overview of the training neural network, training a model is a iterative processes. In each iteration with training data, the model makes a guess. I'm explaining about inside of this forward and backward operation. So first, it makes a guess on the training data and output. The output it is called forward operation, and then you calculate the error on its guess using a loss function. Then you correct the derivatives of the error with respect to its parameter. It's like a backward operation. Then you optimize the parameters using a gradient descent. So this is what training does inside. Then after each epoch, and then you iterate this operation using different mini batches. Then once you finish this order on the training data, you test a model accuracy with a test data like this. Then you shuffle, then you move on to the next epoch after shuffling these samples. Then before I show the example code, I need to explain the several things. The first one is hyperparameters. So hyperparameter is adjustable parameters that let you control the model optimization processes. So different parameter value can impact model training and convergence rates. So we don't lecture how to tune hyperparameter. So depending on how you tune the hyperparameter, it impacts training accuracy or model training time. But we don't cover this hyperparameter tuning. But if you're interested in hyperparameter tuning, this link give you more like explanation on this. Then so this is the major the hyperparameters, number of epochs, the batch sizes, the learning rate. So I think we already explained the number of epochs. Number of epochs is how many epochs you want to run. So you can set one. If you don't want to run longer time, you can just epoch. The number of epoch, that's one. And also in this lecture, we don't have time, so we set a one for epoch. But basically to converge to the certain level of accuracy, you have to run over 10 or 100 epochs to converge. And batch sizes also should be fine. So by changing the batch sizes, it impacts performance or training time, and also impact accuracy. So, but we just specify 64 as the batch sizes. But if you have time, or after this lecture, if you want to try other epoch size and batch sizes, and also learning rate, you can try after these lectures. And the last one is learning rate. Learning rate is to specify how much you want to update a model parameter at each iteration. So smaller value is slow learning speed, like this to converge, whereas large value may result in unpredictable behavior like this. We may not converge to the optimal value to get accurate prediction. So this is trade-off, but normally we specify like this small number, but it's up to this. It's depends on what neural network you train. So this is also you need to train, but in this lecture you specify this number. And then this is our optimization loop on epoch loop. This code shows the iteration of epoch. so that in the beginning of the epoch, it just print out which epoch you're running on. Then you run like first training loop, then you run a test loop. So this is a overview of this source code. So once you set hyperparameter like this at the beginning of the source code, you can then train and optimize your model with optimization loop like this. And in each iteration of the optimization loop is called epoch, as I explained. This is one epoch, and it iterate epochs. And each epoch consists of two main parts. The first one is training loop and test loop. Training loop is to iterate over the training data set and try to converge to optimal parameters. And in the training loop, it iterates over test data instead of training data to check if model accuracy is improving without overfitting to training data set. So this is a source code of this loop. Then I will explain the inside of the training loop and test loop. Inside training loop, optimization happens in 6 steps. First, this is a training loop function. So in each iteration, first you get the mini batch from the data loader like this. So you get, if you specify like this, you get the mini batches one by one. This batch store how many batches you how many samples you trained so far, and X value is a mini batch, Y is levels like answer. Then once you get the mini batch, you call model X to compute a forward propagation that we learned in the last exercise. Then you code loss function. I will explain the detail later about loss function later. But if I briefly explain, we just compute a difference between predicted answer and actual answer. Then you code optimizer.zero gradient to reset a gradient of the model parameters. So gradient by default add up. So to prevent double counting, you need to explicitly call this function to set a 0 at each iteration, like this. Yeah. Then by coding loss.backward, you can run back propagation so that it propagates the prediction loss is to the beginning of this neural network. And then PyTorch deposit the gradient of the loss with respect to each parameter internally. So you don't have to, by coding these things, all the gradient is stored internally. So you don't have to care about how gradient are stored inside. So once you have gradients, gradient, you can call optimizer.step. This is to adjust the parameters by the gradient collected in the backward pass. So by coding this, it update a model parameter and define for the model parameter so that model can increase accuracy little by little in each iteration. And this is the code of this training loop. And also it's not, you don't have to run, but so periodic prints will help you to know the progress of the training. So typically you may want to print progress of this training like this. This example called print the progress in every 100 training data. sorry, this is number of batches. How many? So every 100 batches, batch training, it output. Sorry, it's not number of sample, it's number of batches that you trained so far. And this is the explanation of the loss functions when presented with some training data. Our untrained network it's likely not to give the correct answer, as I showed in the previous exercise. Here, like because we didn't train, the answer is 9, but this neural network gave us a 6. It's correct answer. And loss function measures the degree of dissimilarity of the obtained result to the target value. And it is the loss function that we want to minimize during the training. So it compare loss function. It compare the actual answer and predicted answer, like computer delta value between this value. So if the answer is exactly the same, it gives you 0 value. But if it's not exactly the same, it gives some delta or dissimilarity. By minimizing this delta value, you can get accurate result by in the course of training data. So to calculate the loss, that we make a prediction using input of our given data sample and compare it against the true data level value, as I explained. And actually, there are several loss functions. It has mean square root, mean square errors, negative log likelihood, and also cross entropy loss. And cross entropy is one of major loss functions. So in this lecture, we use cross entropy. So this is a function cross entropy, but you don't have to understand. You don't have to understand this formula. You just want to know how to call this cross entropy loss. The code is like this. So you, by coding this function, you can create a loss function. Finally, not finally, okay. 2 more slides for the exercise. So optimization is the process of the adjusting model parameters to reduce model error in each training steps. Optimization algorithms define how this process is performed. And there are several ways to optimize the parameters. So all optimization logic is encapsulated in the optimization object. And here we use SGD, stochastic gradient descent optimizer, but there are several other optimizer. If you want to interested in other optimizer, I think if you click this one, you will see the list of other optimizers, I think. And the other optimizer include like Adam and RMSP, RMS props. Occasionally, other optimizer works better for different kinds of model and data. So this also can be part of a hyperparameter. By changing optimizer, you may be able to get a better answer or worse answer. So we initialize optimizer by registering the model parameters like this, and that you need to be trained and passing the learning rate to the optimizer like this. By specifying model parameters and learning rate, you can create SGD optimizer like this. And this is the last slide before the next exercise. In the training loop, you need to iterate over the test dataset to check if model accuracy is improving without overfitting to the training data. So when testing, disabling gradient calculation is useful for inference by coding torch grad when you are sure that you will not run back propagation. So also it reduces memory consumption for computation that would otherwise have required. Otherwise you need to specify for requires grad. So because we only need to, in test loop, we don't train neural network. We just test. That means you only need to run forward propagation. So that's why you don't need gradient. So that you can speed up test loop. This is what we does. You get the size. You can in this train you can just copy. Sorry, you can just copy and paste it for the exercise. So if I briefly explain, you can get I think this side is to for the this size is to to calculate the accuracy, how many data is trained, how many data is correct answer, so that divide the correct answer by the total number of sizes, you can compute the percentage of accuracy. And what it does is we iterate over different tests, then code forward function, then accumulate test loss function value using this. Then you get the average of loss function, the result, so that then it output the loss function result. This is what test loop does. And then what this line it does is, if answer is correct, it increment the number of increment this variable to record how many sample image data can this neural network can give a correct answer for. I think, yes, this is the last exercise for today. So the last exercise is to write a code to train the net one with MNIST by extending 0.3 build nn.py. And I will give like 5 minutes. So hint is, if you just copy and paste to this base source code of this snippet, then you can get this training code. And again, this is this source code will give you the correct source code to train this neural network. But again, we don't have time, so I will do the exercise. No, this is the answer. Need to do. So right now we haven't trained this set. So what we does is we get a data set, and we pass this data set in data loader and print out the first image and first level. Then we define the neural network. We create an instance of neural network, and then we code a forward operation, then predict it, but we couldn't get the correct answer. So what we did is we start training this neural network. So first you need to define hyperparameters. So I also just copy and paste. With a snippet, yes, this one. Just you copy and paste. Maybe it's variable that is used at the beginning. So I will copy and paste here. Then in the previous source code, we specify 64. So we specify immediate number, but we define the variable for mini batch. So we specify variable for mini batch size. We created this variable, so we specify the variable to this argument. Then we already, get the first image and first level answer. We already define network. We create the instance. So what we do is training. Yeah, first you need to, well, order is not that problem, but first you create loss functions. The next one is optimizer. It's optimizer. Sorry. Okay. Let me copy and paste first. This is epoch loop. I define loops. Then it looks weird. Test. Okay. This. Then. Okay. Then we learned how to implement training loops like this. So we copy and paste because we haven't defined training loop. We copy and paste. Well, it looks really messy. Function here, I think. It looks function optimizer. Okay, I hope it works. Let me test. I directly edited by mistake, but okay. Define loss function, define. Oh, I think I haven't created optimizer yet. I think it's a optimizer is not defined, so make sure to create optimizer after maybe loss. After creation of model instance, because you need to specify model parameters. So and also specify learning rate. So you have to create optimizer after creation of models and defining learning rate. And anything else? Yes, I think so. Okay, let's run this code. Now we have 3 minutes. Okay, it looks it's running, and then it output every 100 batches. So hopefully give me an answer soon. You're taking time. Oh, oops. Give me. Oh, I think. Sorry, I didn't. Max, and also one thing I forgot. One thing. I forgot 2 things. First one is I forgot to insert print out. That's why I didn't see the progress here. paste. Like this. And the second one is I did not copy and paste test. Yeah, if you have time, yeah, I recommend you to type one by one, but today we don't have time, so I will copy and paste like this. I hope it runs properly. Size is not defined. Size is not defined. Size, sorry. 75. This size. Okay. Sorry. I also had to copy this line. For this. Now it started and it output loss function value. As you can see, you see the loss function value is decreasing while you are training data. And this is a progress. How many images are trained so far? In total, we have 60,000 images. And the function is sometimes bigger for some reason. I don't know. Oops. Okay, let's see. Okay. Test is also, yes, also because I print every iteration, it prints a lot of test data. But at the end, maybe I should, sorry. Maybe if you correctly copy and paste, print properly, you would get this answer. I will run answer script instead. We got a bunch of answers, a lot. We get the same, almost same data. This is the final accuracy. The accuracy is 67.5%, and loss function is 2. So that this means this neural network accurately predict the images with the accuracy of 67.5%. Okay, so we are running out of time. So I will rest of the lecture I will very quickly explain. So once you finish training by coding this one line of code, you can dump the training parameters like this, and you can just quickly. So if you add this save function, like if I copy this, difference is just one line or for the one line. So that if you run this code, you can save the neural network parameters. Then the output is same. It just dumped the trained parameter. So I will not show this. While training, I will explain the rest of the stuff. Then, so once you run this code, it output the trained weights, trained parameters as a file. And if you want to use this trained neural network, you load these parameters by coding this and code this function .eval. Then now you can use this trained neural network. So what it does is this. You just add it. So in the beginning, you create it, the model, then you run inference, but it didn't give you a correct answer. But if you run inference, if you load this trained data, it will give you a correct answer. So training is progressing. No, it's not. So once you finish training, it output the training data. And what this script does is, as I showed, it load this training data and then predict it. So let's run it. So the accuracy is still small. It gives you a correct answer or wrong answer. But this time we are lucky, and the correct answer is 2, and it's predicted as 2, so it accurately predicted. But if you run this code twice, it may give you a correct answer or wrong answer, but it gives 0. So yes, so sometimes it still give you answer because its accuracy is not 100%. The training test data is 5, but it gave 0 as answer. So if you want to get more accuracy, you need to create more like deep neural network with a neuron, or you need to use different neural network like resonant 50, or you have to run more epoch. We just only one epoch, so accuracy doesn't increase. So if you train more and more, it will give more accurate result. Okay, this is all the training, and so this time, yeah, as I expected, we couldn't move on to the distributed training, but example code and also training materials is in the rest of the slides. So if you're interested in extending this single code training sample training script into distributed training script, please refer to the rest of the slides. And also your account is available until the end of this school, that is until tomorrow. So after this lecture, if you want to study by yourself, it's welcome. But the node hour allocated to this school is 4,000 node hour. So if you use up all the node hour, you may not be able to use Fugaku anymore. So you can use until you use up all the node hours. Okay, any questions? Sorry, so yeah, 7 minutes extended overrun. But do you have any questions before I close this today's school? Okay, so it seems there are no questions, so I will close this session. And also, if you want to study beyond this lecture, all the material is here, right here on these links. And also, these slides are created based on this URL web page. So if you want to know more details that we couldn't cover in this school, please refer to this web page. Okay, thank you very much for joining today's